Hi, this is Mrs. Baisden, and today we're going to talk about intermolecular forces. So before we talk about specific intermolecular forces, we have to spend a little bit of time reviewing solids, liquids, and gases. So when you're looking at or thinking about the state of matter, the state that matter is in depends on the strength of the intermolecular forces that are present. So if you have a solid has strong intermolecular forces because it's holding those particles together. Other properties of solids is they have high density, they have a definite shape, definite volume, they're not easily compressible. So what that means is their particles are close together already, so there's not space between them to make them get any closer. And when you have a solid, they can be described as being a crystalline solid or an amorphous solid. A crystalline solid has a very rigid structure where an amorphous solid does not. A liquid then has high density, an indefinite shape, but a definite volume, and liquids have moderate intermolecular forces. So the particles are not as close together, they're not held as tightly, but it's still not easily compressible. There's not a lot of space in between those molecules. Finally, we have a gas, which has low density, an indefinite shape, and very weak intermolecular forces. So there's not a great force of attraction between those particles, so they're very spread out from each other. There's lots of space in between the particles, so they are described as being highly compressible. Next, we can look at changes in state. So if you want to write down the changes in state on the space that I left in your notes, you can do that. If not, we're going to come back around to this later where we actually quantify the energy involved in changes in state. But if you notice, as you're going from a solid to a liquid to a gas, there is energy, you have to put energy into the substance for that to happen. If it goes in the opposite direction from a gas to a liquid to a solid, then heat is going to be released. If you're going from a liquid to a vapor, that's actually called vaporization. Evaporation, the term they have listed here, is actually vaporization at the surface of a liquid. And then if you go straight from a solid to a vapor, that's called sublimation. Then going in the opposite direction, if you go from a gas to a liquid, that's called condensation. A liquid to solid is freezing, and then straight from a gas back to a solid is called deposition. So the activity we did in class the other day reviewed or actually kind of introduced intermolecular forces. So general definition of an intermolecular force is the force between molecules. So remember, when we're talking about intermolecular forces, we are talking about the forces that are between neighboring molecules. We're not talking about intramolecular forces. So these would be intramolecular forces. We're not talking about those. We're talking about intermolecular forces. So the force that keeps this molecule next to a neighboring molecule. The way I have the notes set up is from weakest to strongest. When we did the activity in class, they were kind of mixed up, but we're going to start with the ones that are the weakest and then move forward from there. So the first type of intermolecular force we want to talk about is something called London dispersion forces. London dispersion forces are found in all molecules, but they are most important when you are talking about nonpolar molecules. And I gave you a sheet yesterday that kind of reviewed the difference between a polar molecule and a nonpolar molecule. We'll review that a little more in class because it's going to be important to be able to identify whether something's polar or nonpolar in order to classify the types of intermolecular forces that are present. So for London dispersion forces, those are the ones that are important when you have nonpolar molecules because those are the only intermolecular forces that are present. What causes London dispersion forces is the constant movement of electrons. So the electrons are in constant movement, they're constantly moving around the nucleus, and at any given time, you could have more electrons on one side of the atom than the other. When that happens, it creates what's called a dipole or an instantaneous dipole. So you have an instant where you have a partial negative and a partial positive. So and in this particular example, it's because these two electrons happen to, for just an instant, be on the left side of that atom. As soon as they move to another place, then that instantaneous dipole is gone. When that happens, though, when you have an instantaneous dipole, that can then cause induced dipoles in neighboring molecules. So if you have a partial negative here, that's going to repel any electrons that are close to that in the neighboring molecule, and then that's going to create a partial negative and a partial positive in that one. Then when that happens, it does the same thing to the next neighboring molecule. And again, remember, these are very, very short-lived. So this happens in an instant, and as soon as those electrons shift, this is gone. So as a result of that, these are the weakest of the intermolecular forces. Here's an example that just shows how those instantaneous dipoles can then cause induced dipoles. So you can see how when one has the instantaneous dipole, the partial negative, it then repels the electrons in a neighboring atom, and it starts a quick little chain reaction. But again, remember, this is very quick. These happen and then they go away, which is why they're not very strong. There's a lot of factors that go into dispersion forces and the strength of dispersion forces when you are talking about different nonpolar compounds. So if you have just a nonpolar compound versus a polar compound, then the nonpolar compound has a weaker intermolecular force. But if you're talking about a bunch of nonpolar compounds and you're trying to order those in terms of intermolecular forces, you have to consider a couple different things. So when we talk about something called polarizability, that's the tendency of an electron cloud to distort. So what that means is that's the tendency of this molecule to have instantaneous dipoles and potentially induced dipoles. So polarizability is affected by a couple things. The first thing it's affected by is the numbers of electrons. So the more electrons something has, the more polarizable it is. So the more electrons you have moving around, the more the potential for those electrons to end up in kind of a lopsided position that would create that instantaneous dipole. Shape is another example, and there's some pictures on the next slide here. But if you have something that's longer and skinnier, those are more polarizable because there's more surface area and more potential to come in close contact with a neighboring molecule. So if it has an instantaneous dipole, if it has more surface contact or potential surface contact with a neighboring molecule, then it's more likely to create that induced dipole in the next molecule over. The last one is molecular weight. An increased molecular weight has larger electron clouds, and those are easier to polarize. So the larger the clouds, the more room those electrons have to move around, the more potential for your instantaneous dipoles. So there's on the left, you can see the table of the boiling points of the noble gases. So as the molar mass of that noble gas increases, its boiling point increases. And then over on the right, you can see the surface area issue that we talked about. So in this first example up here, you can see that there's a lot of area there where those two molecules could be in close contact with one another. So the polarizability of those is much larger than these down here because there's not as much potential contact or closeness between them. Here's another example where you can see how all of these compounds are made out of carbon and hydrogen. So these are all nonpolar compounds, but you can see as their molar mass increases, their boiling point increases. And again, that's because there's a greater potential for polarizability as that molar mass increases. Okay, the next type we need to talk about are things called dipole-dipole forces. So just as a reminder, a dipole is a permanent area of positive charge and negative charge. So back in the London dispersion forces that we just talked about, that was something that happens and then goes away. When you're talking about polar molecules, which is where dipole-dipole forces are found, that's a permanent area of partial positive charge and partial negative charge, which you can see by the picture down there. These molecules are attracted to one another as a result of these dipoles. And when you're looking at relative strength of things that have dipole-dipole forces, the more polar the molecule, the more significant the interaction. So the greater the difference in electronegativity of those atoms that are involved, the more polar it is, and then the stronger those forces are going to be. Something that's related to this is a property called miscibility. Miscibility is basically will two things mix together. So miscibility, by definition, is the ability to mix without separating into two states. So the easiest way to remember this is that like dissolves like. So if you have a polar substance, it's going to mix with another polar substance. If you have a nonpolar substance, it's going to mix with another nonpolar substance. If you have two substances, that one that's polar and one that's nonpolar, you're going to get a situation like you have down here. So in this case, the C5H12 is my nonpolar substance. Water is my polar substance, so you can see in the picture here how they kind of separate out. They will not mix together. So this is kind of that classic oil and water that you see or you might have seen in your refrigerator when you have salad dressing that separates out. Another good example of this is if you've ever eaten something that is really, really spicy or really, really hot or has like hot peppers in it, that hot pepper oil that causes that heat sensation is a nonpolar compound. So if you try to drink a lot of water to relieve that sensation, it's not going to happen because water is polar and that oil is nonpolar. So it's not going to do anything to dissolve that compound. The best way to relieve that is to eat or drink something that is the same type of compound, so something that is nonpolar. So something like milk, if you eat any kind of dairy product that has that nonpolar property, that's going to help to dissolve that oil and then get rid of the pain that you're experiencing. A special type of dipole-dipole interaction is something called hydrogen bonds. So hydrogen bonds are found in polar molecules. So this is still under the umbrella of dipole-dipole, it's just a special type. So it's found in polar molecules where hydrogen is bonded to fluorine, oxygen, nitrogen, and in some cases they even include chlorine. So what happens is because FO and N and Cl are all very electronegative atoms, they are really, really good at pulling electrons to themselves. Hydrogen only has one electron, so when it's attached to or it's bonded to fluorine, oxygen, nitrogen, chlorine, that pulls its one electron away. So then hydrogen is just left with a proton all by itself. So that creates a very strong dipole, which then creates a very strong attraction to neighboring molecules with those same dipoles. So these are really strong interactions. So these are stronger than just regular dipole-dipole forces. So you can see a couple different examples here of, in this particular case, there's nitrogen, hydrogen bond, and there's an oxygen, hydrogen bond. So one important thing to remember when you're trying to identify these is for hydrogen bond, first of all, the hydrogen bond is between the hydrogen on one and the oxygen on a neighboring one, or the nitrogen on one and the hydrogen and a neighboring one. So the ones that I'm circling, those are the hydrogen bonds. But in order for that hydrogen bond to be present, you have to have hydrogen bonded to an electronegative element within the molecule. So if hydrogen was bonded to something else in that particular molecule, or oxygen was bonded to something else, and they weren't bonded to each other, that would not create hydrogen bonds. So the hydrogen bond is created because the hydrogen is bonded to a very electronegative element that pulls the electron, and then that creates that strong positive and strong negative on a neighboring atom, and that's what creates the attraction. Okay, the last type of interaction that we're going to talk about is something called ion-dipole forces. These are not technically intermolecular forces because they're not between molecules, they're between a molecule and an ion. But these are stronger than any of the other three, so these would be the strongest that we've talked about so far. And these happen when you have a polar substance, usually water, mixed with an ionic compound. So the reason water is so good at dissolving things is because it is polar. It has a partial positive side and a partial negative side. So what happens when you dissolve an ionic compound in water, you can see all the positive sides of the waters surround the negative ion, and all the negative sides of the water surround the positive ion. So it makes it very good at dissolving substances. Okay, so here's your summary, and this is already in your notes. So dispersion forces are found in everything, but they are important when you're talking about things that are just nonpolar, and the strength depends on a couple different things, molecular shapes and weights and numbers of electrons. Dipole-dipole is our next strongest. These are found in polar molecules, and they add to the effect of dispersion forces, so they're going to be more important when you're talking about polar molecules. Hydrogen bonding is a special type of dipole-dipole. It's found where when you have hydrogen bonded to NOF, and then like we said, sometimes Cl, and those are the strongest of the intermolecular forces. And then we have ion-dipole forces, which are stronger than all of those, and we find those when we have ionic substances mixed with water or other polar substances. So this is a chart from your book, so you can see just another visual of the different types of forces. So the first one, here's your dispersion forces. So you can see those instantaneous and induced dipoles. Dipole-dipole, you have polar molecules that create the partial positive and the partial negative. The hydrogen bonding is that special type when you have hydrogen bonded to fluorine, oxygen, nitrogen, or chlorine. And then ion-dipole is when you have an ion that is attracted to a substance that has dipole-dipole attractions. All right, so let's look at a couple example problems here. So the first example problem says, which molecules have dipole-dipole forces? Now, the answers are given here, and I put those on there so you can see what the structures look like, because sometimes you have to draw structures to figure out whether something is polar or nonpolar. So if you have something that's dipole-dipole, you're looking for polar molecules. So in our discussion of polar versus nonpolar in that chart that I gave you, if you have something that is symmetrical, if you have a molecule that's symmetrical, like carbon dioxide, you can see that even though oxygen is electronegative, it's pulling the electrons away from the center, but with the same magnitude of force. So you've got, overall it cancels the partial negatives out. So there's no dipole forces there because you've got it pulling an equal magnitude on both sides. CH2Cl would be polar because it has 4 things attached, but 2 of them are very electronegative. So these Cl molecule or Cl atoms that are attached there are very electronegative. So what it's doing is it's pulling the electrons to itself, which creates an uneven balance of electrons, which creates the dipole. And then your last example that you have here, this one there would be no dipole-dipole forces present because you have a very symmetrical molecule. So there's hydrogen attached on all sides, so there's no unbalanced sharing of electrons.